Hello everyone, I am Anudaya from BSC first year chemistry honors. Today I am going to read the chapter chemical bonding. So let's start. A covalent bond is formed by mutual sharing of electrons between the combining atoms of the same or different elements. The atoms involved in the formation of a covalent bond constitute equal number of electrons for sharing in order to acquire configuration of nearest noble gas. The pair of electrons which constitute the bond between atoms is called a bonding pair of electrons. If there is one bonding pair of electrons between two atoms, the bond formed is called single covalent bond. On the other hand, two or three pair of electrons between two atoms constitute a double or triple bond respectively. According to Lewis' concept, the covalency of an element is the number of electrons which its atom contribute for sharing while forming a covalent bond. For example, the covalencies of hydrogen, oxygen and nitrogen are 1, 2 and 3 respectively. Now theoretical treatment of covalent bond. The simple picture of covalent bond does not tell us anything about many interesting questions such as arrangements of electrons in molecules, the shapes of molecular orbitals, energy levels in molecules, etc. Like atoms, we can write the Schrödinger wave equation for describing the behavior of electrons in molecules. However, it is very difficult to solve the Schrödinger wave equation for molecules. The solutions can only be obtained by using certain approximations. There, there are two main approaches which are commonly used. These are first is valence bond theory and second is molecular orbital theory. Both these methods are based on the variation principle or method. Now the first theory is valence bond theory. The valence bond theory was put forward by W. Hitler and F. London in 1927. It was later improved and extended by L. Pauling and J. C. Slater in 1931. The basic assumptions of this theory are: first is, atoms do not lose their identity even after the formation of the molecule. Second is, the bond is formed due to interaction of only the valence electrons. As the two atoms come closer to each other, the inner electrons do not participate in the bond formation. And the third is, during the formation of bond, only the valence electrons from each bonded atom lose their identity. The other electrons remain unaffected. Fourth and last is, the stability of bond is accounted by the fact that the formation of bond is accompanied by release of energy. The molecule has minimum energy at a certain distance between the atoms known as internuclear distance. Larger the decrease in energy, stronger will be the bond formed. Now the topic is resonance and resonance energy. The valence bond theory results into concept of resonance. According to valence bond theory, a molecule of hydrogen cannot be represented by a single structure, which could account for the stability of molecule. In fact, a molecule of hydrogen may be described by the following structures which have ionic as well as covalent character. As has been discussed earlier, the actual wave function and the stability of molecule is obtained by suitable combination of wave functions of these structures. In other words, the actual structures of molecule is not represented by any one of the structures but can be represented by combination of these. The contribution of each structure can be determined by its nature and stability. The actual structure of the molecule is considered as resonance hybrid of these structures. The phenomenon is called resonance and the individual structures are called resonating structures or canonical structures. These resonating structures are drawn with double-headed arrows between them. It may be noted that none of the resonating structures have real existence. Also, it does not mean that the actual molecule exists for a certain fraction of time in one form and for another fraction of time in another form. In fact, the actual structure has no pictorial representation. The resonating structures are only a convenient way of picturing molecules to account for all the properties of a molecule. The resonance hybrid may be compared with a mule. For example, like resonance hybrid, a mule has the characteristics of a donkey and a horse. But at no time it is either of these. Thus, resonance may be summarized as follows. When a molecule cannot be completely represented by a single structure, but its characteristic properties can be described by two or more different structures, then the true structure is said to be a resonance hybrid of these structures. This phenomena is called resonance. For example, hydrogen molecule is considered to be a resonance hybrid of above structures marked first, second, and third. These may be represented as follows. The molecule is said to resonate between the three resonating structures. Now the term is resonance energy. As mentioned above, the resonance hybrid is more stable than any of contributing structures. The extra stability of resonance hybrid as compared to most stable having lowest energy of the various resonating structures is called resonance energy. Thus, definition is that resonance energy is thus defined as the difference between the actual bond energy of the molecule and that of the most stable of resonating structures. Thus, resonance energy is equals to actual bond energy minus energy of most stable of resonating structures. For example, the resonance energy of carbon dioxide is 138 kJ per mole. This means that actual molecule of carbon dioxide is about 138 kJ more stable than the most stable structure among the contributing structures. This can be easily illustrated as given below. Now there are rules for writing resonating structures. To explain the characteristic of a molecule, a number of resonating structures may be written. The energies of different resonating structures should be as close to the actual molecule as possible so that the structures have significant contributions. There are certain rules which permit the selection of structures which contribute towards resonance. The following are essential rules for writing resonating structures. Now, the first rule is the contributing structures should have the same atomic positions. They should differ only in the position of electrons. For example, the following two structures of phosphorus acid, that is H3PO3, are not resonance structures because they have different position of atoms in the two structures. Second rule is the contributing structure should have the same number of unpaired electrons. For example, the following three structures may be written for nitric oxide, that is NO. In these structures, third structure is less important than the other two because it has three unpaired electrons, whereas structure first and second have only one unpaired electron. Similarly, we may write three structures for benzene as follows. Obviously, in this case, structure third is unstable because it contains unpaired electrons. Experimentally, it has been observed that benzene does not contain any unpaired electron. Third rule is the contributing structure should not differ much in energy. This can be easily explained by taking the example of benzene. For benzene, five resonating structures may be written as follows. Now the fourth rule is contributing structure should be so written that the negative charge resides on electronegative element and positive charge resides on electropositive element. For example, the three possible structures of HCl are structure third, in which negative charge resides on electropositive element and positive charge resides on electronegative element, is ruled out. Hydrochloric acid is therefore a resonance hybrid of only first two structures. Now the fifth rule is in contributing structures the like charges should not reside on adjacent atoms. This means that contributing structure should be so written that unlike charges reside on neighboring atoms while like charges resides are separated as far apart as possible. For example, resonating structures for nitrous oxide, that is N2O, may be written as follows. In this case, Third structure is not feasible because it places a positive charge on electronegative oxygen and also had same positive charge on adjacent nitrogen and oxygen atom. Similarly, for hydrozoic acid, that is HN3, the following three structures may be written. In this case, third structure is insignificant because of positive charge on adjacent atoms. Now the sixth and last rule is the greater the number of covalent bonds, the greater is the contribution of resonating structures. Thus, the doubly bonded structures, second, third, and fourth of BF3 molecule shown below are important because of formation of an additional covalent bond. Now, there are given some resonating structures of some molecules. So, first is hydrogen molecule, that is H2. The various resonance structures of hydrogen molecule are, as discussed above, are these. Second is oxygen molecule, O2. The bonding in O2 molecule is generally represented as follows. According to this structure, there is a double bond between two oxygen atoms. Each atom has also two unshared pair of electrons. However, in addition to this covalent structures, the ionic structures may also be written. Experimentally, it has been found that oxygen molecule has double bond and paramagnetic character due to presence of two unpaired electrons. Although the above structures explain the bond order of molecule, yet they fail to account for the paramagnetic character of oxygen. As is clear, none of the above structures have unpaired electrons. Thus, the above structures do not explain all the properties of oxygen molecule. To account for the paramagnetic character of oxygen molecule, Pauling suggested a 3-electron bond. The 3-electron bond contains 3 electrons and has bond strength equal to half of the normal covalent bond. It has also one unpaired electron, thus oxygen molecule may be represented by fourth structure also. The above structure has one single bond and two 3-electron bonds. Therefore, this structure accounts for double bond and paramagnetic character of O2 molecule. However, this structure do not obey the octet rule. It may be noted that molecular orbital theory explains the bonding in O2 molecule more satisfactorily. Now the next structure is nitrogen molecule N2. Nitrogen molecule has the following resonating structures. Contributions of second and third are relatively less. Now the fourth is carbon monoxide molecule CO. The simple structure of carbon monoxide may be written as follows. However, this structure does not explain the various characteristics of molecule as discussed below, in which first is bond length. In the above structure, there are two covalent bonds between carbon and oxygen. The carbon-oxygen bond length has been experimentally determined by X-ray diffraction to be 1.13 angstrom. The normal CO bond length is known to be 1.22 angstrom and CO bond length is 1.10 angstrom. This means that bond between carbon and oxygen in carbon monoxide is not a double bond, but it is closer to a triple bond. Therefore, carbon monoxide has been proposed to be a resonance hybrid of following structures. Bond length measurement suggests the structure third should predominate over first and second because it has a triple bond. Now the second factor is dipole moment. According to third structure, there is positive charge on oxygen atom and negative charge on carbon atom. Therefore, the molecule should have appreciable dipole moment from oxygen to carbon, but experimentally the carbon monoxide molecule has very low dipole moment, that is 0.12. This suggests the contribution of second structure also. Structure second has dipole moment from carbon to oxygen. This reduces the polarity of molecule due to structure third. Therefore, as expected, carbon monoxide has very low dipole moment. Now the fifth structure is carbon dioxide molecule, that is CO2. The simple electronic structures of carbon dioxide molecule are as follows. These structures are justified on the basis of following facts. First is bond length. First structure suggests a double bond between carbon and oxygen. The carbon-oxygen bond length in carbon dioxide has been found to be 1.15 angstrom. The normal C double bond O bond length is 1.22 angstrom and CO bond length is 1.10 angstrom. This suggests that carbon-oxygen bond in carbon dioxide molecule is in between double and triple bond. This means that there must be some contribution from second and third structure also, which have triple bond also between carbon and oxygen. Now the second factor is dipole moment. It has been observed that dipole moment of carbon dioxide molecule is zero. This means that contribution of second and third structure must be equal so that net dipole moment of molecule comes out to be zero. The contribution of second and third structure may also be indicated by energy considerations. The energy of a carbon-oxygen double bond is 731.5 kJ per mole. If structure first is only possible, heat of formation of carbon dioxide molecule should be 731.5 into 2, that is 1463 kJ per mole. CO2 molecule has two C double bond O bonds, but experimental heat of formation has been found to be 1601 kJ per mole. The difference between these values suggests that the actual molecule of carbon dioxide is 138 kJ more stable than the structure first. This accounts for the contribution of structure second and third. Now the next molecule is nitrous oxide, that is N2O. The nitrous oxide, also known as dinitrogen monoxide molecule, may be represented as the resonance hybrid of following structures. All these structures are polar. Third structure is unfavorable because it has positive charge on electronegative oxygen atom and also has electric charge of same sign on adjacent atoms. Moreover, according to third structure, the molecule should have appreciably high dipole moment. However, NO has a very low dipole moment, in a sense 0.116. This suggests that contribution of third structure to the real structure is less, and the molecule is mainly resonance hybrid of two structures, first and third. These have opposing dipole moments and therefore N2O has very low dipole moment. Now the seventh structure is carbonate ion structure, that is CO3 2 negative. According to valence bond theory, the structure of carbonate ion carrying two negative charges, in a sense two electrons in addition to those present in one carbon and three oxygen atoms, may be represented as. In this planar structure, there are three carbon to oxygen bonds, two of which are single bonds, which the third is a double bond. Evidently, a carbon to oxygen double bond should be a carbon to oxygen single bond. But it is known from X-ray studies that the three carbon to oxygen bonds in carbonate ions are of equal length, which lies in between the usual single and double bond lengths. This observation can be explained on the basis of resonance between three possible structures as shown below. Now there is given limitations of valence bond theory. The main limitations of valence bond theory are: first is the valence bond treatment could be applied successfully to only a few simple systems. In most of the systems, the mathematical treatment involved is very difficult and we have to use approximate methods. Therefore, valence bond treatment is inadequate in many systems. This theory assumes that the two electrons of shared pair constituting the internuclear bond must come from two different atoms. Therefore, the formation of coordination valency could not be explained by this method. Third is, it fails to explain bonding in electron deficient compounds. Fourth is, for any molecule or ion, we have to write several resonating structures, and even then we say that the true structure is none of these but a resonance hybrid of these structures. It is not possible to write one structure which can explain all the structural features of that molecule or ion. Fifth is, according to this theory, the atoms in molecule of oxygen should have electronic configuration resembling neon. This would make the molecule diamagnetic as follows. However, oxygen molecule is paramagnetic, indicating the presence of two unpaired electrons. This theory fails to explain the paramagnetism of oxygen molecule also. Though valence bond theory has some limitations, yet it finds wide applications. It is frequently used as a qualitative guide in predicting the geometry of molecules or ions. Now the topic is directional character of covalent bond. The covalent bond is localized between the nuclei of atoms. The strength of this bond depends upon the exchange of electrons between the two combining atoms. It has been showed by polling that the strength of covalent bond is proportional to amount of overlap of wave functions or atomic orbitals of the two electrons constituting the bond. The bond formed will be strong if there is maximum overlapping of atomic orbitals and there is maximum interpenetration of charge densities of electron involved in the bond formation. Thus, the bond formed by a given orbital will tend to lie in the direction in which that orbital has maximum value. In other words, the covalent bond has directional nature. The directional nature of covalent molecules leads to definite shapes and geometries. The shapes and geometries of molecules can be explained on the basis of two theories, in which first is hybridization and second is valence shell electron pair repulsion theory. Now let's study about hybridization. The concept of hybridization is introduced to explain the shapes of molecule. We have learned that formation of a covalent bond requires one unpaired electron with each of the two overlapping orbitals. This means that the number of bonds formed by an atom depend to some extent on the number of unpaired electrons in the atoms. Therefore, in accordance with the electronic configuration, beryllium is expected to be inert, no unpaired electron and no bond. Boron with one unpaired electron should be monovalent, one unpaired electron, one bond. And carbon with two unpaired electrons should be divalent. However, in their compounds, beryllium is divalent and carbon is tetravalent. Therefore, it is not possible to account for the valencies of beryllium, boron, and carbon on the basis of simple theory of bonding. In order to explain these anomalies, a new concept known as hybridization was introduced. This can be explained by taking the example of carbon compounds. The ground state electronic configuration of carbon, having atomic number 6, is 1s2, 2s2, and 2p6. The outer electronic configuration of carbon may be represented as follows. There are only two half-filled orbitals in the valence shell of carbon, therefore its bonding capacity should be 2. However, in actual practice, carbon exhibits the bond capacity of 4. For example, it is known to form molecules such as CH4, CCl4, etc. This can be explained on the basis of promotion concept. In order to explain the bonding capacity of carbon, it was proposed that one of the electrons from 2s filled orbital is promoted to the 2p empty orbital, which is in a higher energy state. This state of atom is known as excited state and the process is known as promotion. Thus, for half-filled orbitals get formed a valence shell which account for the bonding capacity of 4 of carbon. The configuration of carbon in the excited state is as follows. The above configuration reveals that all the 4 bonds formed by carbon will not be identical. For example, in the formation of CH4 methane molecule, one CH bond will be formed by the overlapping of two s orbitals of carbon and one s orbital of hydrogen, where the other three CH bonds will be formed by the overlapping of 2p orbital of carbon and one s orbital of hydrogen. But actually, in most of the organic compounds such as methane, carbon tetrachloride, etc., all the 4 bonds of carbon are equivalent. The equivalent character of bonds can be explained with the help of a new concept known as hybridization. This may be defined as the phenomena of intermixing of the orbitals of slightly different energies so as to redistribute their energies and to give new set of orbitals of equivalent energies and shape is called hybridization. The new orbitals formed as a result of hybridization are called hybrid or hybridized orbitals. Thus, to form 4 equivalent bonds, 1 2s and 3 2p orbitals of carbon hybridize and formed four new orbitals called sp3 hybrid orbitals. The hybrid orbitals formed have characteristic orientation in space. For example, the four sp3 hybrid orbitals orientate towards the four corners of a rectangular tetrahedron. These four orbitals will overlap with one s orbital of hydrogen to give four equivalent bonds. It may be noted that hybridization is not a real physical process, but it is a mathematical concept which has been introduced to explain the structural properties of molecules. Now there are characteristics of hybridization. First is the number of hybrid orbitals formed is equal to number of orbitals. So now the topic is characteristics of hybridization. The number of hybridized orbitals formed is equal to number of orbitals that get hybridized. Second is the hybridized orbitals are always equivalent in energy and shape. Third is the hybrid orbitals are more effective in forming stable compounds than the pure atomic orbitals. And the fourth is the hybrid orbitals are directed in space in some preferred directions to have stable arrangement. Therefore, the type of hybridization gives the geometry of molecule discussed later on. Conditions for hybridization are: first is only the orbitals present in valence shell of atom are hybridized. Second is the orbitals undergoing hybridization should have only a small energy difference. The orbitals which greatly differ in energies cannot take part in hybridization. Third is promotion is not an essential condition prior to hybridization. And the fourth and last is it is not necessary that only half-filled orbitals participate in hybridization. In certain cases, even filled orbitals of valence shell participate in hybridization. Now there are types of hybridization. There are many types of hybridization. This not only involves s and p orbitals but d orbitals also. The different types of hybridization are discussed below. First is sp hybridization. In sp hybridization, one s and one p orbitals mix and form two equivalent sp hybrid orbitals. The linear geometry of molecules such as BeCl2, BeH2, and BeF2 can be explained on the basis of sp hybridization as described below. According to valence bond theory, the formation of a covalent bond requires one unpaired electron with each of the two combining atoms. This means that bonding capacity of an atom depends upon number of unpaired electrons in the atoms. Therefore, beryllium is expected to show no valency because there is no unpaired electron in its atom. However, beryllium exhibits divalency in its compounds such as BeH2, BeF2, and BeCl2, etc. To account for the divalency of beryllium, one of the electron from 2s orbital is promoted to the next available vacant 2p orbital as shown ahead. Now this state of atom is known as excited state and the process is called promotion. Now there are two unpaired electrons and beryllium will form two bonds. But the two bonds thus formed will not be equivalent because one bond will be formed by overlapping of 2s of beryllium and 2p of fluorine, while the other will be formed by overlapping of 2p of beryllium and 2p of fluorine. But experimentally it has been observed that both the beryllium fluorine bonds in BeF2 are equivalent. To account for this, it is assumed that one 2s and one 2p orbitals of beryllium hybridize to form two equivalent sp hybrid orbitals as shown below. These two sp hybrid orbitals, trying to remain as far apart from each other as possible due to repulsive forces, adopt linear arrangement making an angle of 180 degrees between the two orbitals. Now fluorine atoms has the configuration 1s2, 2s2, 2p, x2, 2p, y2 and 2p, z1. One of the orbitals is evidently half-filled. This half-filled p orbital of each fluorine atom overlaps with one of the half-filled sp hybrid orbitals of beryllium atom. In this electron sharing process, each orbital contains two electrons and beryllium fluoride, BeF2, is formed. This is represented. The bond angle in BeF2 molecule is 180 degree, so the geometry is linear. It may be noted that each hybrid orbital consists of one large lobe and one small lobe. The large lobe, it may be noted, is much bigger than the original p orbital. It enables it to bring about a higher degree of overlapping with the orbital of reacting atom. Example fluorine. As a result, the bond formed is very strong. Now the second type of hybridization is sp2 hybridization, in which one s and two p orbitals hybridize to form three equivalent sp2 hybrid orbitals. This can be illustrated by considering the example of Bf3 molecule. Shape of Bf3 molecule. Electronic configuration of boron is 1s2, 2s2 and 2px1. Since boron is trivalent in compounds, it is assumed that one of the 2s electrons is promoted to the next vacant 2p, in a sense 2py2 orbital. Therefore, the excited state of boron has three unpaired electrons. Now, to form three equivalent bonds, the three orbitals 2s, 2px and 2py hybridize to form three sp2 hybrid orbitals. These three sp2 hybrid orbitals, trying to remain as far apart as possible, adopt trigonal planar arrangement, making an angle of 120 degree. The mixing of three atomic orbitals, one 2s and two 2p. These three hybrid orbitals formed are directed towards the three corners of an equilateral triangle. Each of these sp2 hybrid orbitals has one-third s character and two-third p character. Now the next type of hybridization is sp3 hybridization. In sp3 hybridization, 1s and 3p orbitals hybridize to form sp3 hybrid orbitals. This may be illustrated by considering the formation of methane molecule. The carbon in the ground state, having atomic number 6, has configuration 1s2, 2s2, 2px1 and 2py1, has only two unpaired electrons. To account for tetravalency, it is assumed that one of the 2s electrons is promoted to vacant 2p orbital, in a sense 2px orbital. To account for equivalent CH bonds, one 2s and three 2p orbitals hybridize to form sp3 hybrid orbitals, as shown below. Now the next type of hybridization is sp3d hybridization. This involves the mixing of one s, 3p and one d orbital. The geometry of pf5 can be explained on the basis of sp3d hybridization. The outer electronic configuration of phosphorus, the central atom, is 3s2 3p3, which may be represented. It has three unpaired electrons in the ground state. In order to explain pentavalency of phosphorus, one of 3s electrons is promoted to higher energy 3d orbital so that it has five unpaired electrons in the excited state. These orbitals are hybridized to give five sp3d hybrid orbitals arranged in trigonal bipyramidal geometry. Then each of the sp3d hybrid orbitals overlaps with the 2p orbital of fluorine, forming 5 pf bonds. Having trigonal bipyramidal geometry, it may be noted that d orbital involved in sp3d hybridization is 3dz square. Now the next type of hybridization is sp3d 2 hybridization. In this hybridization, 1s, 3p and 2d orbitals are mixed. The geometry of SF6 molecule can be explained on the basis of sp3d2 hybridization. The electronic configuration of sulfur atom is 3s2 3p4. In the ground state of sulfur, there are only two unpaired electrons. To account for 6 bonds of sulfur, one 3s and three 3p electrons are promoted to higher energy empty 3d orbitals. These 6 orbitals, one 3s, three 3p and two 3d, get hybridized to form 6 sp3d2 hybrid orbitals. These 6 orbitals are directed towards the corners of an octahedral. Each of these sp3d2 hybrid orbitals overlaps with 2p orbitals of fluorine to form SF6 molecule, which has octahedral geometry. In this case, unlike trigonal bipyramidal structure, all the 6 bonds are equivalent and all the bond angles are equal to 90 degree. Next type of hybridization is sp3d3 hybridization. This involves the mixing of 1s, 3p and 3d orbitals. The geometry of IF7 can be explained on the basis of sp3d3 hybridization. The outer electronic configuration of central atom, that is iodine, is 5s2 5p5. It has only one unpaired electron to make 7 bonds. 1s and 2p orbitals are promoted from 5s and 5p orbital to higher energy vacant 5d orbitals. These 7 orbitals 5s, 5px, 5py, 5pz, 5dxy, 5dyz and 5dzx are then hybridized to give 7 sp3d3 hybrid orbitals having pentagonal bipyramidal geometry. Then each of the 7 sp3d3 hybrid orbitals overlaps with 2p orbitals of fluorine to form IF7 having pentagonal bipyramidal geometry. In this geometry, all the bonds are not equivalent. 5 of these are directed towards the vertices of a regular pentagon making an angle of 72 degrees with one another. The other 2 are at right angles to the plane of first set of 5 bonds. Due to different bond angles, the bonds are different in length. The axial bonds are larger than equatorial bonds. Next type of hybridization is DsP2 hybridization. In addition to above types of hybridization, DsP2 type hybridization is also known particularly for transition metal ions. The orbitals involved in this type of hybridization are d, x square minus y square, s and 2p. The 4 orbitals hybridize to give square planar geometry. Some typical examples of square planar complexes are NiCN4, 2 negative, etc. The common examples of a molecule involving DsP2 hybridization is NiCN4, 2 negative. In this case, the oxidation state of nickel is +2. The ground state electronic configuration of nickel is 3d8 Therefore, the electronic configuration of Ni2 positive is 3d8. When the 4 cyanide ions come closer to Ni2 positive ions, then the 2 unpaired d electrons are paired up, thereby making a 3d orbital empty. These empty 4 orbitals hybridize to form 4 dsp2 hybrid orbitals. Each one of the 4 cyanide groups donate a lone pair of electrons to the vacant dsp2 hybrid orbitals as shown. Now the topic is sigma and pi bonds. We know that a covalent bond is formed by the overlapping of half-filled orbitals of two atoms. The covalent bond may be classified into two types, sigma covalent bond and pi covalent bond. So let's talk about sigma covalent bond. This type of bond is formed by the end-to-end overlapping of two half-filled atomic orbitals. In this case, the orbitals overlap along the internuclear axis and the bond is symmetrical about the internuclear axis. The bond can be formed by any one of the following types of overlapping. First is SS overlapping. This type of overlapping involves the half-filled s orbitals of two atoms. For example, the bond formed between two hydrogen atoms to form H2 molecule. In this case, the 1s orbitals of both hydrogen atoms overlap to form a sigma bond. Second is sp overlapping. This type of overlapping involves the half-filled sp s orbital of one atom and a p orbital of another atom. For example, 1s orbital of hydrogen overlaps with 2pz orbital of fluorine to form a sigma bond between hydrogen and fluorine in HF molecule. Now the third type is pp overlapping. This type of overlapping involves half-filled pz orbital of two atoms. For example, a molecule of F2 is formed by overlapping of 2pz orbitals of two fluorine atoms. Now the second type of bond is pi covalent bond. This type of bond is formed by sidewise or lateral overlapping of two atomic orbitals. The sidewise overlapping can take place when the orbitals have their lobes perpendicular to molecular axis. For example, two px or py orbitals overlap above and below the internuclear axis to form a pi bond as shown below. Strength of sigma and pi bond. In the case of sigma bond, the orbitals overlap end to end and the extent of overlapping is large, but the sidewise overlapping to form sigma bond is not efficient. Therefore, sigma bond is a stronger bond and pi bond is a weak bond. It may be noted that pi bond is present in addition to a sigma bond in molecules containing double and triple bonds. For example, oxygen molecule has a double bond consisting of a sigma and a pi bond. Similarly, N2 molecule contains triple bond, 1 sigma and 2 pi bonds. Let us illustrate the formation of sigma and pi bonds with the help of two examples, ethylene and carbon dioxide. First is formation of ethylene. The trigonal planar geometry of ethylene suggests that in C2H4, each carbon atom undergoes sp2 hybridization. The carbon atom in the ground state has the electronic configuration as 1s2, 2s2, 2px1 and 2py1. In the excited state, one of the electrons from 2s orbital is promoted to nearby 2p orbital, forming 4 unpaired electrons. The 1 2s and 2 2p orbitals get hybridized to form 3 sp2 hybrid orbitals which adopt trigonal planar arrangement. One of the 3 sp2 hybrid orbitals of each carbon atoms overlap with the other carbon atom to form carbon-carbon sigma bond. The remaining 2 sp2 hybrid orbitals of each carbon form 2 bonds with hydrogen atoms. On each carbon atom, one p orbital was left unhybridized and these p orbitals overlap sidewise, forming a pi bond. Thus, in ethylene, the carbon atoms are held together by two bonds, one sigma and one pi. Second example is formation of carbon dioxide molecule. The carbon dioxide molecule is linear and this suggests that the carbon atom undergoes sp hybridization. The ground state and excited state of carbon atom are shown below. Now the next topic is valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory is the simplest theory for predicting the geometries of molecules. It is based on the repulsive interactions between the electron pairs in the valence shell. This theory was proposed by Sidgwick and Powell in 1940 and was finally developed by Gillips and Nylam in 1957. According to this theory, the shapes of molecules can be determined by the number of electron pairs in the valence shell of central atoms. These electron pairs experience electrostatic repulsions from one another, and the bonded atoms in a molecule adopt that particular arrangement in space around the central atom, which keeps them on the average as far apart as possible. Now, here are given postulates of Vesper theory. VSEPR, valence shell electron pair repulsion theory. First is the geometry of a molecule depends upon the number of valence shell electron pairs, whether bonded or not, around the central atom. In the formation of a bond, the central atom shares its valence electrons with the surrounding atoms. However, in certain cases, all the valence shell electrons may not take part in bond formation. The electrons left in the valence shell without forming bonds exist as lone pairs. For example, in methane, carbon uses all the 4 valence electrons in forming 4 bond pairs. On the other hand, in water, S2O, the central oxygen atom has 1s2, 2s2 and 2p4, 6 valence electrons. The hydrogen atom shares 2 of these 6 valence electrons in the formation, leaving 4 electrons as 2 lone pairs. Thus, in methane, there are 4 bond pairs around carbon, while oxygen in water has 2 bond pairs and 2 lone pairs around it. According to VSEPR theory, it is the total number of electron pairs, bonded as well as lone pairs, that determines the geometry of molecule. Now the second postulate is electron pairs tend to repel one another because their electron clouds are negatively charged. As a result, the electron pairs try to stay as far apart as possible to acquire a state of minimum energy or maximum stability. Third postulate is repulsion between the lone pair and lone pair of electrons is different than between the bond pairs or one lone pair and one bond pair. The repulsive interactions decrease in the order. The presence of lone pairs in addition to bond pairs will result in certain distortions in the regular geometry of molecules. Now the fourth postulate is repulsive forces decrease sharply with increasing angle between the electron pairs. They are strong at 90 degree, much weaker at 120 degree and weakest at 180 degree. Now the topic is regular and irregular geometries. The molecules in which the central atom is surrounded only by similar bonded electron pairs will have regular geometries, while those in which the central atom is surrounded by bond pairs as well as lone pairs will have irregular geometries. For example, the molecules such as methane, BF3, PF5, SF6, etc. have regular geometries because the central atoms in these molecules are bonded to similar atoms and there are no lone pairs in these molecules. On the other hand, the molecules such as CS2Cl2, CHCl3, etc., in which central atom is bonded to different atoms, and the molecules such as ammonia and water, which have lone pairs as well as bond pairs, have irregular geometries. Depending upon the number of electron pairs, the molecules have different geometries. It may be noted that presence of lone pair disturbs the geometry as already discussed in case of hybridization. Now there are applications of Vesper theory. Vesper theory provides a simple approach to predict the shape of molecules. The results obtained on the basis of this theory are quite in agreement with those obtained from hybridization concept. This theory is very simple to use. In this theory, no distinction is made between s and p electrons. We take into account only the number of electron pairs present in valence shell of central atom. The basic point is that the electron pairs, bonded or lone, try to remain as far apart as possible to get a state of stability. Let us illustrate this theory by some simple molecules and ions. First is ammonia molecule. In ammonia molecule, the central nitrogen atom, having atomic number 7, 1s2, 2s2 and 2p5, has 5 valence electrons. 3 of these valence electrons share electrons with 3 hydrogen atoms forming 3 bond pairs around the nitrogen atom. The remaining 2 electrons are present as a lone pair. Thus in ammonia, nitrogen is surrounded by 4 electron pairs, 3 bond pairs and 1 lone pair. These 4 electron pairs adopt tetrahedral geometry, but the bond angle will not be 109.5 degree because one of the electron pair around nitrogen is a lone pair. As already explained, lone pair bond pair repulsion is more than bond pair repulsion. As a result, the lone pair of electrons will repel the bond pair strongly and bond angle decrease to 107 degree. The geometry of ammonia molecule is also regarded as pyramidal. Its next example is hydronium ion, that is H3O positive. In this case, the central oxygen atom having atomic number 8 having configuration 1s2, 2s2 and 2p4 had 6 valence electrons. In the formation of hydronium ion, the electrons form pairs with 2 hydrogen atoms and 1 H positive ion, leaving 2 electrons as one lone pair. It may be noted that there is one coordinate bond between lone pairs of oxygen atom and H positive ion. The 4 electron pairs around the central atom adopt tetrahedral geometry. However, due to the presence of one lone pair, the geometry is distorted and the bond angle is not normal tetrahedral angle of 109.5 degree because of larger lone pair bond pair repulsion than the bond pair repulsions. The bond angle decreased to about 107 degree. Now the next theory is molecular orbital theory. Molecular orbital theory was developed by Hunt and Millikan in 1932. The basic idea of molecular orbital theory is that atomic orbitals of individual atoms combine to form molecular orbitals. The electrons in molecules are present in those molecular orbitals which are associated with several nuclei. These molecular orbitals are filled in the same way as atomic orbitals in atoms are filled. So the basic assumptions of this theory are: first is, a molecule is considered to be quite different from constituent atoms. All the electrons belonging to the atoms constituting the molecule are considered to be moving along the entire molecule under the influence of all the nuclei. Second is, just like an atom, molecule has orbitals of definite energy levels. These orbitals are called molecular orbitals. Third is, the molecular orbitals are formed when the atoms to be bonded come close together. The atomic orbitals of these atoms merge into molecular orbitals. Thus, the molecular orbitals are associated with nuclei of all the bonded atoms in a molecule. Fourth is the shapes of molecular orbitals depend upon the shape of combining atomic orbitals. Now the topic is linear combination of atomic orbitals, LCAO. According to molecular orbital theory, the molecular orbitals are formed by linear combination of atomic orbitals of the atoms which form the molecule. The linear combination means the simple molecule consisting of two atoms labeled as HA and HB. Let the wave function for the electrons in atomic orbitals of two atoms A and B be respectively. When these atomic orbitals are brought closer, they combine to form molecular orbitals. The wave function for electron in field of nuclei of atom A and B, in a sense corresponding to molecular orbital, may be written as a suitable linear combination of wave functions of first and second atoms, where Ca and Cb are the mixing coefficients and give the relative contribution of each atomic orbital to molecular orbital. These coefficients are so adjusted that the resulting molecular orbital has lowest energy and maximum stability. In case of homonuclear diatomic molecules such as H2, these atomic orbitals must contribute equally to the molecular orbitals. Thus, in case of H2 or any other homonuclear diatomic molecule, the weights of Ca and Cb must be same as the contributions are proportional to square of their coefficients. For simplicity, if Ca is 1 and Cb is plus or minus 1, so that there will be two molecular orbitals as the result of two type of combinations. The orbitals associated with phi 1 is called bonding molecular orbital, whereas the orbitals associated with phi star is called anti-bonding molecular orbitals. Thus, the number of molecular orbitals formed is equal to the number of atomic orbitals combined. The physical picture of bonding and anti-bonding molecular orbital can be obtained by considering the atomic orbitals. To illustrate this, we may take the combination of 1s orbital of one hydrogen atom with 1s orbital of second hydrogen atom to form two molecular orbitals in hydrogen molecule. As discussed above, there are two ways of combining atomic orbitals. The molecular orbital formed by addition of overlapping of two 1s orbitals. In the case of 1s orbital of hydrogen, the wave function is positive and the two orbitals combine to form a molecular orbital, which is also positive in all regions of space. It is clear from the figure that region between two nuclei where the two 1s atomic orbitals overlap has high electron density. Such a molecular orbital is called bonding molecular orbital. The second possible combination of two atomic orbitals is by subtraction. The molecular orbital formed by subtraction of overlapping of two 1s orbital as shown. In this orbital there is a plane of zero electron density between two nuclei. This is called nodal plane. As is clear, the electron density in this molecular orbital is concentrated in regions away from each nuclei. In other words, it does not contribute to bonding and the atoms HA and HB do not form bonds. Therefore, the resulting molecular orbital is called anti-bonding molecular orbital. These bonding and anti-bonding molecular orbitals are labeled as sigma 1s called sigma bond and sigma star 1s called sigma star. The 1s indicates the molecular orbital is formed from 1s atomic orbital and star is used to represent antibonding. The sign sigma signifies that orbital is symmetrical about the molecular axis as explained below. The term sigma is used for orbitals which are symmetric to rotation about the internuclear axis. For example, if we rotate the bonding molecular orbital through 180 degree, the orbital remains exactly the same. Similarly, the anti-bonding molecular orbital sigma star 1s is also symmetrical to rotation or rotating the molecular orbital through 180 degree, it also remains unchanged. Thus, we have noticed that a bonding molecular orbital has high electron density in the overlap regions, whereas the antibonding molecular orbital has no electron density in between the nuclei. This may be graphically illustrated by plotting sigma square, omega square, in a sense electron probability density of orbitals of two hydrogen atoms against the internuclear distance. The electron probability density for 1s atomic orbitals of the individual atoms are shown by dotted lines when the probability densities of 1s atomic orbital of both the atoms are added. The probability density functions for bonding molecular orbital is obtained. It is shown by solid lines. It is clear from the figure that there is greater probability of finding the electron between the two nuclei than for the separate atoms. On the other hand, anti-bonding molecular orbital is formed by subtraction of electron probability densities the two atoms. It is clear from the figure that the electron probability density of two atomic orbitals get cancelled in the center so that there is no probability of finding the electron in the region of this inner sense between the two nuclei. This corresponds to nodal plane as already mentioned. This can also be shown by simple mathematics. We know that electron density or probability density in a molecular orbital will be proportional to square of wave function. Now for the bonding molecular orbital, where omega 1 and omega 2 are the wave functions for the individual atoms, the probability density of the subtracting the electron in molecular orbital will be as follows. Now the topic is relative energies of bonding and anti-bonding molecular orbitals. We have learned that in case of bonding molecular orbital, the attraction of both nuclei for the electrons is increased. This results in lowering of energy. In the case of anti-bonding molecular orbital, the electrons try to go away from nuclei and this corresponds to repulsive state. The energy of this orbital will be higher. The relative energies of bonding and anti-bonding molecular orbitals along with atomic orbitals can be represented as follows. Thus, the bonding molecular orbital is stabilized relative to energy of the isolated atoms and anti-bonding molecular orbital is destabilized relative to individual atoms. Further, it may be noted that bonding molecular orbital is stabilized to the same extent as the anti-bonding molecular orbital is destabilized in the case of homonuclear diatomic molecules. Now there are differences between bonding and anti-bonding molecular orbitals. The main points of differences between bonding and anti-bonding molecular orbitals are as follows. Bonding molecular orbital is formed by the addition of overlap of atomic orbitals, while anti-bonding molecular orbital is formed by the subtraction of overlap of atomic orbitals. Bonding molecular orbital has higher electron density in the regions between two nuclei of bonded atoms, while anti-bonding molecular orbital has lesser electron density in the region between the two nuclei of atoms. In bonding molecular orbital, the forces in this tend to bring the two nuclei of atoms together. Therefore, the electrons in bonding molecular orbital contribute to attraction between the two atoms, while in antibonding, the forces push the nuclei apart. Therefore, the electrons in antibonding molecular orbital contribute to repulsion between the atoms. In bonding molecular orbital, it possesses lower energy than the isolated atomic orbitals, while in antibonding, it possesses higher energy than the isolated atomic orbitals. Now, there are conditions for combination of atomic orbitals. We have learned that molecular orbitals are formed by the effective combination of atomic orbitals, but all types of orbitals cannot combine with each other. The following are main conditions for effective combination of atomic orbitals. First is the energies of atomic orbital involved should not differ much from one another. The combining atomic orbital should not differ much in energies. For example, in case of homonuclear diatomic molecules of the type A2, 2s orbital of one atom can combine with 2s orbital of another atom, but 2s orbital of one atom cannot combine with 2s orbital of another atom. In the case of heteronuclear diatomic molecules of the type AB, however, such combinations may be possible. Second is, the atomic orbitals combine only if they overlap to considerable extent. The extent of overlap between atomic orbitals of two atoms should be large. Third is, the combining atomic orbital should have the same symmetry about the internuclear axis. In other words, in order to form a bonding and anti-bonding molecular orbital, either the symmetry of two atomic orbitals must remain unchanged when rotated about the internuclear axis, or both atomic orbitals must change symmetry in an identical manner. For example, a 2s orbital of one atom can combine with 2s orbital of another atom, but it cannot overlap with 2px or 2py orbital of another atom. For example, when 2s orbital of one atom A overlaps with 2px orbital of another atom B, uh, plus overlap cancelled by the plus minus overlap. Plus plus overlap is cancelled by the plus minus overlap. As a result, no molecular orbital is formed. In other words, such a combination is not possible. However, it may be noted that 2s orbital of one atom can also combine with 2px orbital of another atom because both have same symmetry about the internuclear z-axis. Now there is comparison of valence bond and molecular orbital theories. The valence bond theory and molecular orbital theory are the two basic approaches to explain the structure and bonding in molecules. They have some similarities as well as differences. These are given below. Similarities of valence bond and molecular orbital theories. Valence bond and molecular orbital theories have the following similarities. First is, both the theories are approximations. Second is, both the theories take into account the overlapping of atomic orbitals. The strength of bond depends upon the extent of overlapping or interaction. Third is, the basic principles involved in the distribution of electrons are similar. Thus an orbital, whether atomic or molecular, cannot have more than two electrons. Pauli's exclusion principle. They are filled in the order of increasing energy of Bohr's rule. If there are more than one vacant orbitals having the same energy, they would first be filled singly. Hund's rule. Fourth is, in covalent bond formation, the essential interaction, according to both the theories, is the sharing of bonding electron density by both nuclei. Both the theories predict the concentration of electron density between the nuclei. Fifth is, both the theories predict that for bonding the atomic orbitals must overlap and have appropriate symmetry about the molecular axis. Both the theories account for directional nature of covalent bond. Now there are points of differences. Valence theory. It starts with individual atoms and considers the interaction between them. While in molecular orbital theory, this theory states that the nuclei of constituent starts with the nuclei of constituent atoms. Electrons in molecules are localized as if they are present in isolated atoms in case of valence bond theory, while in molecular orbital theory it treats the nuclei of molecules as polycentric and then constructs the molecular orbitals. In valence bond theory, the atoms retain their individual identity, while in molecular orbital theory, the atoms lose their identity. In valence bond theory, resonance is an integral part, while in molecular orbital theory, it does not involve the concept of resonance. In valence bond theory, for most of the molecules, underestimates the ionic term and does not give it much importance, while in molecular orbital theory, overestimates the contribution of ionic terms in its total wave function. Valence bond theory cannot explain the paramagnetic nature of O2 molecule, while molecular orbital theory explains the paramagnetic nature of O2 molecule. Now here are bonding parameters. Covalent bonds are characterized by certain parameters such as bond length, bond angle, bond order, and bond energy. These are discussed. First is bond length. Bond length is defined as the average distance between the centers of nuclei of two bonded atoms in a molecule. It can be determined with the help of X-ray diffraction analysis. If the substance is obtainable in crystalline form. Otherwise, the bond lengths are determined with the help of spectroscopy or other techniques. It is usually expressed in angstrom units or picometers. For example, the bond length between two hydrogen atoms in a hydrogen molecule is 0.74 angstrom. The bond lengths of some simple bonds are given. It may also be noted that bond length decreases with increase in bond multiplicity. Thus, C triple bond C bond length is shorter than C double bond C bond, which in turn is shorter than C single bond C bond. This is expected because the increase in atomic number in the group. The distance of valence electrons from nucleus increase successively with the addition of a new shell. In other words, the size of atoms increase along a group and consequently the distance between the bonding nuclei, bond length, increase. Second is bond angle. Bond angle may be defined as the average angle between the orbitals containing bonding electron pairs around the central atom in a molecule. It is expressed in degrees, minute, second. Bond angle gives an idea about the distribution of orbitals around the central atom in a molecule and therefore determines the shape of a molecule. For example, the HCH bond angle in methane is 109 degree to 28 degree. The HOH bond angle in H2O is 104.5 degree and HNH bond angle in ammonia is 107 degree. Third term is bond order. Bond order is defined as the number of covalent bonds present between two bonded atoms in a molecule. The bond orders of 1, 2 and 3 corresponds to single, double or triple bonds. For example, in hydrogen molecule, the bond order is 1 because two hydrogen atoms are joined by one covalent bond only. Similarly, oxygen molecule has bond order of 2 and nitrogen molecule has bond order of 3. Bond order is inversely proportional to bond length. The higher the bond order value, the smaller is the bond length. For example, the bond length in nitrogen molecule is shorter than that of oxygen molecule. The bond length values of some common molecules having multiple bonds are given as follows. In compounds with partial multiple bond character or delocalized pi bonding, bond orders may be fractional. For example, C bond C. Distance in ethane is 154 picometer and bond length for C double bond C bond in ethylene is 134 picometer. But C single bond C bond length in benzene is 136 picometer. This indicates that carbon-carbon bond in benzene is between single and double bonds. With this value, the bond order has been calculated to be 1.67. Similarly, carbon-carbon bond length in graphite is 142 picometer and this value corresponds to bond order of 1.53. Fractional bond orders have been observed in molecules showing resonance. Bond order has also great influence on the stability of a molecule. The stability of a molecule is measured by its bond dissociation energy. The higher the bond order, the largest is the bond dissociation energy. For example, nitrogen molecule with triple bond has larger dissociation energy than oxygen molecule with double bond. Now the fourth term is bond energy, bond dissociation energy. We have learned that when a bond is formed between the atoms, energy is released. This means that bonded atoms have lesser energy than the separated individual atoms. Obviously, the same amount of energy will be needed to break the bond. This is called bond dissociation energy and is measure of bond strength. It may be defined as the amount of energy required to break 1 mole of bonds of a particular type between the atoms in the gaseous state. It is generally expressed in terms of kilojoule per mole. For example, the bond dissociation energy of hydrogen-hydrogen bond in hydrogen molecule is 458 kilojoule per mole. Similarly, the bond dissociation energy of chlorine to chlorine in Cl2 is 242.5 kilojoule per mole. Larger the bond dissociation energy, stronger will be the bond in the molecule. The bond dissociation energy of simple bonds are given. So this is the chapter of chemical bonding.